in the series of the ISI AI seminar. So yes, I would like to introduce a little bit about our lab, the Signals Lab, which is short for Social Intelligence for Generative Networked Adversarial and Large-Scale Systems at the USC Information Sciences Institute, and led by Professor Luca Luccheri. And we are relatively new, but highly interdisciplinary and collaborative, consisting of 13 people for now. As you can see in the picture to the left, that we are so collaborative. We're so new that we haven't got a picture yet, but stay tuned for that. Our focus is on computational social intelligence, studying in intersections of generative AI and network systems and adversarial operations to address pressing challenges like AI trustworthiness and influence campaigns. So yes, it is also my great pleasure to introduce our speaker for today, Dr. Gianmarco de Francisci Morales, who is a principal researcher at CENTAI. Dr. Morales is a globally recognized expert in computational social science and data mining, known for his incisive work on social media polarization and his significant contribution to the Apache Software Foundation. And today he's gonna present his timely talk, Learning Agent-Based Models from Data. He will be showcasing his innovative research on transforming traditional agent-based models, or ABMs, into probabilistic generative models. This powerful approach allows researchers to leverage large-scale data to enhance the predictive power of ABMs with applications ranging from opinion dynamics to understand complex systems. So it is now time to begin, and please show me a very extending welcome to Dr. Morales, and off to you.
Thank you so much for the kind introduction, and thanks for having me here. Let me share my screen. Let's see. You should be able to see my screen now. Yep, cool. All right, thanks so much for having me here. Thanks for the introduction. And as David kindly introduced, today we'll be talking about opinion dynamics models, which is one of my main interests. I've been studying polarization, echo chambers, and these are the kind of models that are used to describe these phenomena on social media that we have studied empirically. And so I want to start by focusing on the word models. Everything in science is a model, but no model is true. We know this. This is what you see on the screen is the Ptolemaic model of the solar system, and it is wrong. It puts Earth at the center, but it was used back in the days for a number of applications. Then in the 17th century, Kepler used data compiled by Tycho Brahe to mitigate Copernicus' theory that the sun is at the center of the solar system. And ideally, that's how science works. So you have models and you have better models that supplant the previous ones. And I argue that if you want to develop something that's a computational social science, we need to bring our models up to scientific standards. Now, as I was saying, like opinion dynamics models usually are agent-based models. So ABMs are basically systems of autonomous agents that evolve over time according to some predefined rules. And these rules encode some, in our case, sociological assumptions. In other, in economics are different kind of assumptions. In ecology and different kind of fields they're used. So these systems are simulated to draw some conclusions. So they are kind of a simulation. Let me give you a small example here. What you can see is the very first ABM by James Sakoda, who studied segregation pattern in US Japanese internment camps during World War II, and then he was interned there. And then later in 78, Schelling repurposed the model to study segregation, racial segregation in US cities, and this is how we know the model, by Schelling's model. So you have a grid which represents a city, and there are two types of agents, red and blue. And then each agent has a satisfaction number, which is a number of neighbors with the same color. And if the satisfaction is lower than parameter tau, which measures its homophily, then it relocates to an empty spot on the grid. And then the simulation goes on. The surprising result here that Schelling is famous for is that even with a small homophilic preference, you just need to have want one third of your neighbors to be the same color as you, then you can get the segregation that you saw in the animation. So you don't need to be extremely racist to create segregation, let's say, at the individual level. And um, now the question is, are ABMs really scientific models? So on the plus sides, they are mechanistic models. In the example I just gave you, I explain exactly how individual homophily creates a global system segregation. So they are at the highest rung of the ladder of causality by Pearl, and we can ask counterfactual questions and what-if scenarios, basically. On the negative side, I didn't mention data in anything that I just described. So data is actually not part of the equation. In particular, there is no sound way to fit parameters for this type of models. And my argument here is that if data is not part of the equation, then how do we falsify theories? How do we basically do the thing that I explained at the beginning? How this is one of the cornerstones of Popperian philosophy of science. So how do we improve our knowledge? So let's look at the relationship between ABMs and data. Initially, ABMs were born as theory development tools. So these they were encoding some sociological theory, for example, and it was used to derive some implication of this theory that's or the hypothesis encoded in the model. However, as is this covering? Can you see the whole screen? Or
Yeah.
yeah, okay, cool. As the people basically started using them more and more, they started using as forecasting tools as well. So, for example, you may be aware that epidemic models used during COVID were indeed basically ABMs. So did they use them with real world data? They set the parameters of these models with a process called calibration. So what is calibration? Calibration is, I like to call it poor man's estimation, and the idea is you run simulations with different parameter values until the model reproduces some kind of summary statistics of the data that you're trying to model. That's it. And if this looks a bit less than ideal, then you are not alone. In particular, there are three, I think, major problems. The first one is that this procedure doesn't give you any parameter significance. It's difficult to do model selection. All the statistical things that you are used with other models are not available. The second one is that the choice of the summary statistics and the distance measure used to compare the data are completely arbitrary, and different choices might lead to different results. And the third one is that this is a manual, expensive, and error-prone process, and it's expensive, especially if the models are complex to simulate. Now, here I'm giving a kind of a sketchy summary of these. Of course, there are more complex techniques, but in practice, what people do in projects that involve ABMs is this. The question is, can we do better than this? Well, of course, otherwise I wouldn't be here talking to you. So I'll outline here the proposal, and I promise this is the only math you'll see in the talk. So the core idea is to rewrite ABMs as probabilistic generative models. So the state of the system, which is X, is drawn from some probability distribution, which is parameterized by some theta, which are the parameters that you want to fit. and the whole history of the system, so everything that happened before. So this is the most general form, of course. Then you can have more specific shapes that allow you to do more things. Once you have these, you can write the likelihood of the parameters given the data. So this is a function of the parameters. Given it is a function of parameters, you can optimize it, and you can use machine learning, which is basically just gradient descent, and use especially auto-differentiation, which is the sauce behind the neural networks and deep learning, to optimize these parameters. This is very, very simple and high level the whole proposal. Quick historical aside, maximum likelihood estimation was invented by Fisher, and it dates back to the 18th century. And Fisher introduced it as an alternative to the method of moments, which, as you may know, is you fit a distribution by fitting the moments of the distribution, like a summary statistics. And he criticized the arbitrariness in the choice of moment equations, which sounds exactly like what I said before. So I'm not actually telling you anything new here. I have a quick recap of autodiff. I think most of us nowadays are familiar with the automatic differentiation. Just to bring everybody on the same page in case somebody is not, these are a set of techniques that is used to evaluate the partial derivative of a computer program. So you write your computer program that computes functions, and then you can automatically take the derivative of this function by using the chain rule to break complex expressions. And then you can use these, for example, to compute the derivative of your loss function with respect to the parameters, and then take gradient steps to minimize your loss function, and so change the parameters to do that. And it's different from numerical and symbolic differentiation. So it's what allowed people to train big, large neural networks. So how does our proposal solve the problems I highlighted before? So for the first part, the first problem was no parameter significance. Now we have a probabilistic model. So we can inherit all the history, the very long and rich history of probabilistic modeling, and use all the tools that have developed for these models in order to do parameter significant model selection and so on and so forth. The second thing was the arbitrary choice of the loss function, basically. And now we have instead data likelihood, which is a principled approach to tie probabilistic models to data. And third, instead of having this manual expensive process, we can use automatic differentiation and avoid running thousands of simulations just to fit the parameters of these models. Now, this is the general idea, and the rest of the talk I'll show you a few examples that we have been working on. And again, if you have any questions, please feel free to interrupt me. So first things, we're gonna see how this likelihood-based approach compares to the traditional simulation-based approach, what I called calibration before. And we're gonna look at opinion dynamics models, so how people's belief evolve. As I said, they're used to model polarization, radicalization, echo chambers, and the idea is to take data from social media. So the application scenario we have in mind is to take data from social media and use this data to fit these opinion dynamics models. In particular, we will use the bounded confidence model. It's one of the most well-known opinion dynamics models. The idea is that every agent has an opinion in -1, 1, 0, 1, depending on how you want to parameterize, and then agents interact with each other. And if the opinion of the other agent is close enough to your own opinion, then the two agents converge towards some middle ground. So you can see the equations here. They're very, very simple, and they describe exactly what I just said. It has been used in many, many different theoretical studies and in some empirical studies, not many. We want to bring it closer to data. So when I said that was the only math in the talk, I lied, clearly. There is another bit of math. Uh, I don't want to go into the details of how you write the ABMs into a generative model. I just want to show you that it's not that complicated, and the likelihood function here is something that you can write in a single line. So a lot of people that I talk to, explaining this approach are really scared about this step, which is admittedly not super easy. Not It's the hardest part of the approach, but it's definitely doable for a lot of agent-based models, especially in opinion dynamics. So basically the idea here is if you see the generative model, the only part I want you to focus on is that there is this epsilon. Epsilon is this confidence bound, so the parameter that tells you how far you need to be from another agent at most in order to have a positive interaction that brings you closer to each other. And this is what we want to estimate in these experiments. So what we do is we launch a bunch of simulation with simulated data with the real model. Then we fit the parameter on these real traces, or on these simulated traces, both with simulation and likelihood-based methods, and we see which one does better. So let's start with this macro parameter inference. Here you can see that you have on the x-axis, you have the true epsilon that we use to generate the single data trace. On the y-axis, you have the estimated epsilon with this method of simulated moments, which is the calibration methods. And you can see that, it does reasonably well. And, taking into account this is a very simple model. This is what the likelihood-based approach does. And if you want to quantify, the 90th percentile relative error is almost 90% for the simulation-based approach and about 22% for the likelihood-based. And this is because, of course, these are small values. So if you make a mistake of, 0.1 or a value that is 0.1, it's a very, very large error. So I would say that likelihood-based approach clearly works better. So not only it's more accurate, so if you see the error that we commit in estimation is much lower, but it is also faster. And the more data we have, so the longer the data trace, the better it is, of course. So this is great, but it's not the only thing we can do. Because we have this likelihood-based inference, we can also start assuming that we don't see other pieces of the data. So for example, assuming we don't see the initial opinions, we can actually recover the initial opinions. So this is the initial opinion of the users, and here we only assume that we see the interaction. For example, I see another person retweeting, one person retweeting another, I can assume this is a positive interaction, and then I can reconstruct the opinion dynamics of the trace. And again, the more data we have, of course, the longer the data trace, the better is the recovery of these initial opinions. So by looking at this opinion dynamics model as a probabilistic generative model, we can actually start thinking about observed and latent variables, which is something that is not done in agent-based models, and start understanding which ones are actually recoverable. And now let's move actually to an application to real Reddit data. To do this, we complicated a slightly bit the bounded confidence model. We introduced also repulsive behavior. So the idea is that when you have an interaction with a person that is too far from you in opinion space, you have a negative interaction. And a negative interaction basically pushes people farther apart from each other. And this is a controversial effect that some people have found in lab studies. Other people instead were not able to reproduce. But we thought this would help in a social media contest. And so basically by setting the parameters of this model, which are these epsilon plus and epsilon minus to different values, we can have different opinion trajectories. And for example, if we set this epsilon minus, which is the amount of the distance where you have like the amount of the latent parameter opinion space, where you have a negative interaction to some very large value, you have these high contrast scenarios where everybody diverges and you have polarization. If you set the epsilon plus to a large value instead, you have these high acceptance scenarios when everybody converges to the same opinion, which is the typical things you see in simulations of this kind of systems. So again, I will not go into the details of the math, but the idea is you can rewrite this as a probabilistic model. You have these step functions which are replaced by some smooth approximation of these step functions, so some sigmoid functions, and these allow you to write the likelihood and automatically optimize the objective function as a mixtures of sigmoids, which is much easier to deal with than the step function. And the scenario here that we are considering is a very real scenario on Reddit. So we see the presence of interactions. So we see people that comment on each other, but the signs here are latent. So we don't know if the interaction was a positive interaction or a negative one. And the opinions of the users are also latent. So we don't know what their opinions are. Can we learn the dynamics and the parameters of the system? This is the learning problem. Again, we have maximum likelihood approach. Here is a bit more complicated because we have these signs that are discrete. So we use a EM expectation maximization algorithm. Again, I don't want to bother you with the details, but the general idea is the following. We can actually recover the synthetic data. So if we do the same thing as before, even with this more complicated model and by observing a subset of what actually happens in the system, we can obtain the original initial opinions of the users, and we get a good reconstruction of the data traces. We can recover the parameters that generated these traces. So here you can see basically just the various scenarios that we considered for the simulations. And you can see that the high acceptance configuration is the one that has the highest likelihood. So it's the one that is the highest likelihood when we're using that set of parameters to generate those synthetic data tracers. So this means that we are able to do model selection and recover the correct parameters that generated synthetic data. And now we fit it to Reddit data. And the thing here is we had to figure out a way to validate this approach, of course, because we don't really know the opinions of the user. So what we did was the following. We looked at the number of upvotes on the comments. And this is not something that we're using in the model. The model has never seen the number of votes and comments. But we take it as a proxy as to how much a user is appreciated in a given subreddit, right? Now, we estimate the latent positions of users and the subreddits. There's a piece of the model I didn't show you, but just trust me, in opinion space. And so now we have, if a user is close to 1 and a subreddit is close to 1, then they're close to each other. And then we measure this distance in opinion space that the model has learned, and we correlate it with the number of upvotes that the user gets in that subreddit. And what we see is this nice linear relationship. So the x-axis is latent, and the model has never seen anything from the y-axis, but still we see basically that this opinion space that the model has learned, which was completely latent, we learn only from the interactions, is actually predictive of something else that the model has never seen. And this to me is kind of the holy grail. We are able basically to predict something that happened on social media by using a real opinion dynamics model. So this is basically the goal of this line of research. One of the problems with this is, as I said, the tricky part is actually writing the likelihood function. Now, the likelihood function is easy to write for these kind of systems like opinion dynamics, but if you go towards economics, the agent-based model that they use in economics, in econometrics, they are much more complicated. They have pages and pages of equations, And even though we have done it, we have some results, we have some papers on models of um, housing markets. This is much harder, so it took us a much longer time to write the correct likelihood equation and then optimize it. So it's much more complicated. So this brought us to a different approach and asking whether we can do something better. So this is this variational approach that I'm going to talk to you about. So as I said, likelihoods are hard. It's easy to make mistakes when you write them, and it takes a lot of debugging to figure out whether you made a mistake in the implementation or in the math. And it requires a very deep understanding of the data generating process, which I argue it's a good thing anyway, because it's good to know what you're modeling, but sometimes it's too complicated. So the question is whether there is a way to actually avoid it. The answer is variational approximation. So what is variational inference? It's a Bayesian technique that is used to approximate intractable probability integrals. So it's an alternative to Monte Carlo sampling. Now, when you have a probabilistic model, you can use maximum likelihood, which is a frequentist approach, to basically find the maximum of the function. Or you can use a Bayesian approach where you can take the expectation of the parameters with respect to the data. And so the expectation is an integral, and this is where this Monte Carlo sampling of integrals or the variational approximation to these integrals comes into play. So basically, instead of taking the mode of the posterior, we are taking the expectation of the posterior. The trick with variational inference is that a lot of these models have a completely intractable posterior, so it's impossible to write it down properly. And the idea is to write an approximation of the posterior. So we postulate a variational distribution, which is a tractable parametric family. So basically, you assume that your posterior is a normal, for example. And then you optimize the parameters, these variational parameters of this normal distribution by minimizing the KL divergence between the real posterior and Q. And there is a lot of magic and math that goes inside it. Again, I'm not going to go into the details, but this is basically what makes variational autoencoders, if you're familiar with them, work. So again, we go back to the original idea. We transform inference into an optimization problem, and given that it is an optimization problem and we have distributions that are parametric, we can use automatic differentiation to optimize these parameters. So the general schema of the approach is the following. We have the original ABM. We rewrite it as a probabilistic generating model, so we follow the same approach as in the previous papers. Then instead of deriving the likelihood of the PGM, we just use a variational inference engine. We fit the data into it, and what we get is approximate posterior for macro and micro parameters of our model. So this is the general idea. I know it might be a bit vague, but it's intentionally vague because I don't want to explain how the variational inference works. What we did was try it on a large set of different models or variants of the BGM. I'm going to show you the one that is the most interesting, at least in my opinion, which is this BCM with backfire and roles. So each agent can be, in this model, can be a leader and a follower. So this is basically a way to model influencers versus the general public. And the idea of this model is that in the leaders have a different set of parameters, and they can influence the followers, but they are not easily influenced. And this is basically implemented by having a very small confidence intervals for the influencers. Um, so basically, the model will have 4 different parameters, 2 latent macro parameters per role. So one for the positive interactions and one for the negative interactions for each leader and followers. And then it will have set of binary microparameters per agent. So we assume that these roles are not given. So we want to find out from the interactions whether each user is a leader or a follower. And importantly, as we will see, it's important for the results, we assume the number of leaders is, of course, much smaller than the number of followers. Okay, so let's go directly to the results. We have the same kind of plots that I showed you before. So on the x-axis, you have the real or the simulated, let's say, data parameter. Each point is a different trace, and on the y-axis, the estimated parameter. And as I said here, in the macro parameters, we have 4 different parameters. On the left side, you have the follower parameters, and on the right side, you have the leader parameters. Top side, positive interaction, bottom side, negative interactions. Here we are comparing with ABC, which is approximate Bayesian computation, which is the Bayesian version of the calibration simulation-based approach that I showed you before. And then with Markov chain Monte Carlo, which is still a probabilistic generative model-based solution, but is not stochastic variation. So it's a different approach. And as you can see, most of the probabilistic generative models based approach do very well on the left side, on the follower side, because there are way more followers. On the right side, you can see that there is some bias, and this is due to the smaller number of examples that the leaders provide, because the leaders are involved in fewer interactions. And you can see that the 2 biases are towards the bottom for the negative and towards the top for the positive. ABC, which is the standard in these kind of studies, is completely off the mark. I mean, there is some correlation, of course, between the parameters, but the values are completely off the mark. And this is something that, we use a package that is used by the Bank of Italy to calibrate their own economic models. So, this is what it's used actually in practice. Here you can see the error rates for the roles. So now we have, instead of these macro parameters, you have these micro parameters, 1 per each agent, and we have to decide whether the agent is a leader or a follower. And you can see the higher the number of interactions, the better is the recovery of the parameter. But as you can see, ABC has a very high error rate, about 0.5, which is almost random. And MCMC works better if you give it enough data. And stochastic variational inference, which is the approach we propose, is much better. Here, I didn't mention there are 2 different versions, one normal and one with normalizing flows. These are the 2 variational distributions that we are using. One is just a normal one, and the other one is normalizing flow, which is a deep learning technique to transform any distribution into a normal distribution. And the cool thing is that we are also much faster, especially with the normal one, which is much easier there is no neural network to train in between. We are much faster than both ABC and also MCMC, which is a very, it's a reasonable approach because it still uses this idea of transforming the ABMs into a probabilistic generative model. But and this is the reason why variational inference was invented. Sampling is much slower than optimization with the current algorithm that we have at our disposal and the current machinery that we have at our disposal. This is basically the pipeline that we recommend people use and that we're using in applied projects inside CENTAI, using variational inference with simple distributions, and it it has proven to be very effective. Now, before concluding, I just want to give a bit of a small rant on model thinking and how machine learning has changed the way we do work. So as you can see, as you have seen during the presentation, we use a lot of results and techniques from machine learning and especially deep learning. As I said, variational inference, automatic differentiation, and also the probabilistic generative modeling part. And these are impressive tools that have been used by a lot of people with great results. However, it seems to me that a lot of the focus in our community is on prediction and using machine learning as a predictors, which is what it does, rather than understanding. I would argue that when we do this, we undermine the goal that I mentioned at the beginning of trying to make our models more scientific, because we need to understand why things happen in order to do science. So understanding that something is a predictor is not enough. My favorite example here is always the size of your t-shirt is a very good predictor for whether you are obese or not, but I wouldn't want it in my causal model because that's not how it works, right? It's not how the world works. So we need to clarify the theories that go into our models and help use the models to develop the theories, which is something that we are not very good at doing. And there is a lot of focus on explainability of deep learning models, which is, it helps, but it's not a substitute for focusing on only prediction. And in particular, when we only throw predictors like the t-shirt size that I just mentioned into the models, we cannot use causal inference. We cannot infer causal relationship just by throwing more data at a model. We need scientific models that stand outside statistical models and inform their generation, their production, their writing, their design. And this is what I call model thinking. So when we look at models for social media, for computational social science, I would argue that we should always be thinking about the data generating process. So if we have some data that we want to write a model for, we should ask ourselves, how was this model, this data generated? What was the human process behind it? We should use model first thinking as a justification for the scientific claims that then we want to make in our articles. And as much as possible, I would encourage us all to use causal models if we can, if it's possible, and possibly mechanistic models, for example, ABMs. And now, thanks to these new techniques that we are developing, we have the ability to use data with ABMs and have the best of both worlds, I would say. And we should always try to use scientifically significant statistical models and try not to use strawman models. So my concluding the presentation, I would say that today we have seen how we are able to fit agent-based models, and especially from opinion dynamics, as if they were statistical models by rewriting them as probabilistic generative models. Once we've done this, we can learn the latent variables of these models. We can play also with different latent variables and apply these models in real-world scenarios on social media. These will improve the forecasting of the model, the prediction, and allows us to do real-world model selection. And my hope is that this line of work will enable us to use data to figure out which model really works, as in the story I told you at the beginning of the talk. In order to bring ABMs and in general all the computational social science models in line with the statistical models and especially with the scientific ones, and make computational social science a real science. Thanks. That was the end of the talk. And if you are interested in this kind of research, Here are a few references, and you can find more on my website.
Thanks so much for a great presentation, Gianmarco. Yeah, let's open the floor for questions. I already see that Luca has the first one. Please ask away.
Yeah, I was trying to find the button to upload, but I was not successful in this. Great talk, Gianmarco, very intriguing. I want to start from your last discussion about model thinking. Um, because I want to know your take on using LLMs as models in combination with ABM. You've been talking about data generating process, so it was always in my mind asking you, okay, what about using those systems? Given that nowadays there's a sort of transition from agent-based modeling to LLM-powered simulation. And you touched many times this concept of generation, content generation, and so I wanted to have a sort of discussion about that and know your take about these. And a more granular question is about the concept of prediction versus explainability. So if you can talk also about that when discussing your take on LLMs. And in more specific terms, I was also wondering, and that I appreciate your knowledge that the prediction is not enough. I completely agree with you, but I'm also interested in the predictive capabilities of your model. What can be done? What are the limitations? And what do you expect can be done with LLM-powered simulation? What you expect can be the limitation on this? Sorry for the
Okay.
extra long question. I can unpack it if needed.
No, I think it's a great question, and I absolutely agree with you. So let me try to take it step by step. So first thing first, LLMs. So actually, no, let me take the other one. It's easier. Here. Here, this is the model. If you look at the right, you have x0, which is the vector of opinion for the users, xt, the vector of opinion at time t, xt plus 1, and you have s. Are the signs of the interactions. So this is what we observed. So the data that we are observing is a graph. So we're assuming that we're modeling retweets, for example. And this has been my bread and butter for the last 10 years. I've been using social graphs and the signals embedded in social graphs. Why? Because basically the NLP tools were not there and they were not good enough and they were not multilingual enough and so on and so forth. Now we have LLMs, so things are changing. So I absolutely love the idea of, instead of having S as an observation, having text and S as an observation. And given that we have generative models for the text, we can embed those into a more global generative model of the whole social media interaction. Whether you say something, you upvote somebody else, you respond to a specific comment, you interact with some other people who have also said something, and use those to drive the inference. So if you can imagine a bounded confidence model where instead of generating just the signs of the interaction, we generate also the text that is driven, conditioned on the opinion, then this is my goal. And in fact, we recently wrote a project proposal about that. The tricky part, that the scientific part that needs to be done is, okay, how do I drive the LLM? How do I put these two things together? How do I drive the LLM? By telling them, okay, you are, I don't know, on the opinion space of gun control, you are 0.7. What does it mean to be 0.7? And so how do I combine the theory that comes from the ABMs with the data generation, with text generation from LLMs. So this is the tricky part to do. There is a lot of work on persona-based generation, for example. So for political affiliation, it kind of works, but there is still a lot of work to be done there. And once you have that, you can train a model end to end by feeding it social media data with text and inferring the opinion of agents, of users, from the text, and then assuming that your BCM is what happens, so how the opinions evolve, then you can see the whole evolution of the people. Now, I do not believe the BCM is the model, the truth. As I said at the very beginning, every model is wrong. However, by looking at this graph, it tells me that at least it's not completely wrong. It tells us something, and there is a reason it's very used, and it's not only because it's very simple to analyze, which the physicists like a lot, but it's also because there is some lab empirical evidence from lab studies that something like this is what's going on. Now, in terms of predictive capabilities, as I said here, for example, you can see that these has some predictive capabilities on completely unseen data. We have another study that I didn't talk about here, where we can actually forecast very well the system. So it can actually, if you drive the system, so if you make the system, the simulation evolve over time, by using our approach to ground the system into the latent variables and using the estimation techniques that I talked about, the forecast is much better. So assuming that the model that you're using represents the reality, using this kind of estimation techniques can make your forecasts much, much better and more accurate. One thing I want to stress here is that what we are proposing here is not that these models are the right models or of reality. What we are trying to propose is a way to compare models, because up to now everybody did their own ABM and say, oh, look, I can generate cleavage, polarization, I can generate this kind of social phenomena by using these rules. And then you have another ABM that does the same thing with completely different rules, and there is no way to tell which one is better. By using data, we hope to actually start being able to run comparison across different models and tell you which one is actually better at explaining the observed data. So while, in my rant, I said, no, look, prediction is not the only thing. Prediction is one of the fundamental things. But you also need to tie it together with the theory that comes from the ABM. So if your prediction is tied with the theory that is encoded in the agent-based model, then I think you have the best of both worlds. I don't know if there was some other aspect of your question that I didn't cover, but please.
No, that's great. In a way, I'm happy we are facing similar challenges to the one that you said, in somehow incorporating the LLMs into this pipeline. But yeah, you covered everything else. I want to leave the room to everybody else for some other questions. But thank you for now, Gianmarco.
I think there's questions from the chat. I can read it out loud from Philip. So it seems like this approach works well for the Reddit case. Do you test it with other scenarios? What you say are the main limitations, I'm guessing, for cross-platform for your approach? Yeah.
So thanks for the question. Yes, we tested it. So the difficulty with testing this approach is that, as I said, we are not testing the model, you're testing the way to fit the model. And by using it on real world data, we had to figure out some way to validate it. When you do it with simulations, you know the ground truth. And so that's a lot of the testing that we have been doing. Of course, when you do the simulations, you also know that the data is generated by the model that you're using to fit. So there is no misspecification. We have done some recent studies on misspecified models, and we've compared with data simulation. which is a Bayesian technique, Kalman filters, smoothers, if you know them, that are used in meteorology, for example, in climatology. And the likelihood-based approach is much, much better, always in this opinion dynamics model. We tested it with the data, for example, from London and Turin, I think was, for this economics model of the housing market. And there, at a certain point, we ran into the issue that the model, the agent-based model, was not realistic enough. And we were not able, for example, to reproduce realistic patterns because, for example, it didn't take into account of buying versus mortgage versus renting. And so basically it was not rich enough to reproduce the real price variations that you see in the housing market. So the limitations I think here are, of course, you need to have a model that is able to explain your data, but just the realization that the model was not good for data was interesting because that model had been published by one of our co-authors as a way to model the housing markets. And when they realized, okay, we can't do that, then it's not the fitting procedure here that the problem is the model itself. This is something kind of closing the feedback loop between data and models. This is exactly what we wanted to do with this kind of this line of research. There are limitations in terms of fitting. For example, the likelihood part is very hard to write in this economic model. It was very difficult to do. It took us more than 6 months to write the whole thing, swapping approximations and so on and so forth. So that there is a bit of art there. Although we're also working on trying to automate that. The variational approach I explained is a step in that direction. There is still, there are still sometimes models that cannot be fit. So there are identifiability problems that can surface where you cannot really recover the parameters that generated some data with that data alone. And this is something that we have a paper that has just been accepted where we look at exactly the limits of identifiability with this maximum likelihood approach. And for the BCM, what we showed is that epsilon is fine, so the bounded confidence is fine, although there might be some slight bias. For the other parameter, which I didn't talk about, which is mu, which is the speed at which you evolve the opinion. So is this mu on the bottom, right? For that one, the maximum likelihood estimation is not even estimator is not even defined, and so you can't use that approach. I mean, you can use it, but then all the statistical theorems don't apply, and so you are you have no guarantee on what you are doing.
Thanks, Gianmarco. I hope that addressed Philip's question. There's another question from the audience in the chat. Why the model does not see the interactions between agents? Any link with game theory?
So here in different models, so the model is this one, but then we can basically hide some information from the model every time to see what happens. And this is to model some realistic data that we have. So in this one, for example, we saw the sign of the interaction. So here, for example, we were thinking about Twitter. In Twitter, when I retweet somebody, of course, people say it's not an endorsement, but we take it as an endorsement. So the sign is always positive. So when we see an interaction, we also see the sign. In the other model instead, which is this one, where is it? There it is. In this one, the sign S here is latent. As you can see, it's not grayed out because here we're thinking about Reddit. And in Reddit, an interaction is I write a comment to something that you wrote. And now I don't know if I'm agreeing with you or I'm disagreeing with you. We could have used some, NLP to try to figure it out, but again, we didn't. This was before LLMs, so we didn't want to do that. And in any case, it's much harder to generate text than to generate the sign of an interactions. As for the game theory part of the question, I'm not sure if there is a relationship with game theory here. I don't see it right away because this is just a dynamic system. So there is no intelligence inside the agents that's take into account what the other people are doing. Of course, you could make the agents rational agents that are game theoretical, and then you would have a game theoretical agents inside the simulations, and then you would have to do all the relation. But not in this case. In opinion dynamics, most of the models, like 90% of the models, don't do that.
Thanks, Gianmarco, and I hope that also address the audience question. If there's any other question, I think we are at time. Yeah, thanks so much, Gianmarco, for a truly fascinating and insightful presentation. And please join me, everyone, in offering a final virtual round of applause for sharing his pioneering work on ABMs today with the ASI AI seminar. And have a good rest of your day, everyone. Thank you.
Thank you so much for having me, and it was a pleasure. If you're interested, just shoot me an email.
Thank you all.